Okay, let us take an example, see how it goes, how it helps us, these properties help us in evaluating integrals. So, suppose we put some m which is a rational number, because only rational powers we have defined. You can take also real numbers whenever it is well defined, but it should be a continuous function and so many other things. So, just to avoid we make it simpler, let us take that m is a rational number in the form p by q or okay. So, now suppose 0 is less than a less than b. So, that means you have the interval as 0 somewhere a and somewhere b. Then you take a to the power b integral of x to the power m with on this interval a to b. So, that is the power function is x to the power m, which is defined on this interval, m is a rational number. Then you take the integral of x to the power m. So, it is integral a to b x to the power m, a dx symbol is missing here. So, that is equal to b to the power m plus 1 minus a to the power m plus 1 divided by m plus 1. So, to show it means we have to really compute, find the Riemann sum, take the limit and see that it happens, right. But let us see how do we proceed. We take a partition of the interval a to b, which is x 0 less than x 1 less than x n, which is b. Suppose this is a partition, and let us take or fix any I in between this 1 to n. Okay. So, that means we are fixing a sub interval x I minus 1 to x I. So, there let us define the function g x equal to x to the power m plus 1. So, this is a clever way of avoiding how to evaluate the abstract limit of the Riemann sum. So, we have done it in another problem earlier, while integral of cosine x we had found out. So, now let us say g x equal to g of x equal to x to the power m plus 1 for x in x I minus 1 to x I. Now, g prime of x is equal to m plus 1 x to the power m. So, it is differentiable, g is differentiable over the open interval. For any point in the open interval, we know its derivative, it is g prime x equal to m plus 1 into x to the power m. So, we apply mean value theorem on g to see that g of x I minus g of x I minus 1 equal to g prime at some point between x I minus 1 to x I, call that c I, times x I minus x I minus 1. So, there is a point c I in every sub interval x I minus 1 to x I, such that this thing happens. Now, what do we do? In our Riemann sum, we take these c I's as our points of the choice set or choice points. So, take these c I's as the choice points. Then what happens? With this c I's, our Riemann sum is equal to summation I from 1 to n. Here it is f of c I into x I minus 1. So, now what is that? It is f of c I into x I minus 1. This is inside the Riemann sum S f p c, summation symbol into this one red underline. And this we compute from x I to the power m plus 1 minus x I minus 1 to the power m plus 1 is equal to m plus 1 times, because of this g prime c I equal to m plus 1 times x to the power m. So, g prime c I equal to m plus 1 into c I to the power m. This is your g prime of c I times x I minus 1, right, and this is equal to m plus 1 times f of c I into x I minus 1. Therefore, f of c I into x I minus 1 equal to the left side x I to the power m plus 1 minus x I to the power m plus 1 divided by m plus 1. So, this becomes the Riemann sum. Now, you want to sum it. So, what will be the sum? M is not dependent on I, we take it out, 1 divided by m plus 1. Then sum of all these numbers, it is x I is varying. So, it appears the first sum looks like x 1 to the power m plus 1 minus x 0 to the power m plus 1. then plus x2 to the power m plus 1 minus x1 to the power m plus 1, it continues up to the nth one. So, you see that this minus term remains, but this one is cancelled. All of them will be cancelling except the last term, which is xn to the power m plus 1 minus something, that minus is cancelled. So, we get xn to the power m plus 1 minus x0 to the power m plus 1. But xn is equal to b and x0 equal to a. So, you get b to the power m plus 1 minus a to the power m plus 1 divided by m plus 1, which is this one, right, which we wanted to show that it is the integral. But for our choice points Ci specifically chosen this way, we see that the Riemann sum itself becomes a number. So, therefore, in the limit the same number stays. So, we get integral to be equal to b to the power m plus 1 minus a to the power m plus 1 divided by m plus 1. So, this trick will be helpful whenever you have a very complicated function and you cannot really do anything through the limits, you apply to the mean value theorem for the differentials. Otherwise, it may not be required. Sometimes we just get it from the function itself, how to evaluate the limit. Okay. So, let us check another example. Evaluate minus 1 to 1 2 plus 3x square plus 4x to the power 5. Okay. So, we apply the previous example and our properties. First thing is integral of 2 constant function dx, it is means 2 into x to the power 0. So, that gives, or directly you can get from our property that integral of minus 1 to 1 to 2, which 2 goes out and it is 2 into b minus a, which is 1 minus 1, it is 2, that is equal to 4, right. Now, we go slowly for the other one, integral minus 1 to x square, because x square is involved. So, that is equal to b to the power m plus 1, which is 1 to the power 3 minus a to the power again 3 divided by 3. So, that gives 2 by 3. And similarly, if you take x to the power 5, that gives power 6. So, 1 to the power 6 minus 1 to the power 6 by 6, and that turns out to be 0. Okay. So, our integral will be this integral plus 3 times, because of property 2, plus 4 times this integral, and now it is easy to simplify and see that the answer is 6. So, now you see how the properties help us from integrating a polynomial if you know how to integrate the powers x to the power n. Okay. So, here we are asked, let us see the third example. Find the area of the region in the first quadrant. So, we want to compute the area of something in the first quadrant enclosed by the parabola y equal to x square. So, it looks something like this, y equal to x square, and the line x equal to root 2. So, say this is root 2. So, this is the area we want to compute, right. So, this area will be equal to integral, we know the integral, right, and then we can find out. So, it is integral 0 to root 2 x square dx, and it is the curve bounded by this. So, 0 to root 2 x square dx. Now, we know how to integrate x square, it is just x cubed evaluated at root 2 and 0. So, root 2 to the power 3 minus 0 to the power 3 divided by 3, that is 2 root 2 by 3. Okay. So, let us take one more example. We want to show that integral of square root of 1 plus cos x over the interval 0 to 1 is smaller than 1.5. So, it is an estimation. Somewhere we have to use some estimation, that is what we will do. So, now you see for x in 0 1 closed interval, cos x is always less than 1. I think that gives, that is why we do. So, then square root of 1 plus cos x will be less than square root of 1 plus 1, which is root 2. So, f of x is less than or equal to g of x, where g of x is equal to root 2, a constant function here, which we can readily integrate, right. So, the integral of 0 to 1 this will be less than integral over 0 to 1 root 2 dx, which is root 2 times 1 minus 0, it is k times b minus a, that gives root 2 and root 2 is smaller than 1.5. So, sometimes these numbers can be different, then you do not know which inequality to apply, but only trial and experience give you some way how to do it. So, we have chosen cos x minus 1 here, not any other inequalities, right. Okay. Let us go to fifth problem, the fifth example. We want to find the mean value of this function on the interval minus 2 to 2. So, the mean value is 1 divided by b minus a integral a to b f of x dx. So, straightforward we can find the integral. So, now what we want is, this is our integral is integral minus 2 to 2 square root of 4 minus x square divided by b minus a, which is 2 minus 2. This is the integral we want to compute. But what is this integral really? So, y equal to square root of 4 minus x square is a circle, it is a circular arc, it is a semicircle really, the square root is positive only. So, it lies on the upper half plane, and square root of 4 minus x square. So, that means its center is at 0 and radius is say 2. So, now you see x square plus y square equal to 4, that gives you y equal to square root of 4 minus x square, right, that is the curve. So, we know its area of this semicircular region, which is equal to 2 pi, right, because radius is 2. So, it is phi into r square, that is of the full circle. So, half circle will be this, that is equal to 2 pi. Then the mean value of this is equal to 2 pi divided by this 4, which is pi by 2. So, now since we know the area, we proceeded this way instead of computing the integral directly, right. Okay. So, let us take one more, say find the values of a and b, so that the integral a to b x minus x square dx is maximum. See what happens here is integral a to b, suppose you have the interval a to b is given, you take any function f of x, then integral a to b f of x is a number, right. But here it is asking, it is not given that what these values of a and b are, they are unknowns. So, this number, which is the definite integral, will depend on both a and b. So, the question is to choose a and b in such a way that this is the maximum number you will be getting from that, right. That is what we are being asked. Okay. So, now let us look at the function first. The function is x minus x square, which we can factor as x into x minus x. So, the reason is you have the f of x. So, we are using a very simple argument. Suppose the function is something like this, which has some negative values and some positive values. If we want to maximize the area bounded by the function and the x axis and these two lines x equal to b, so you take a instead of these negative values, you will take a to be here, right, because it needs to be maximum. So, there is no negatives here. That is, if at all the function has both positive and negative values, we should choose our a to be here, okay, and b we do not know till now, but this is the guiding principle of going for that. So, suppose f of x is bigger than 0 somewhere, then we can choose our a like this. But for this function, where it is bigger and where it is smaller than 0. So, this is x into 1 minus x, that is, if you take 0 here, 1 here, you take any point x in between 0 and 1, then one of them is x minus 0, another is x minus 1, one of them will be positive, one of them will be negative, right. This is 1 minus x. So, both will, their product will become positive if it is between this 0 and 1. If it is bigger, say x is here bigger than 1, then 1 minus is negative, but x is positive. So, that will be negative. Or if it is less than 0, then x itself is negative, but 1 minus x is positive. So, it is again negative. So, what we observe is that for 0 less than x less than 1, in between 0 and 1, f of x is positive, otherwise it is negative, right. So, beyond, that is for x less than 0 and for x bigger than 1. So, once we are going to find this integral to be maximum, okay, so we should find out where it is positive. So, that means the picture would look something like, okay, something like this, not exactly, but like this. So, here it is 0, here it is 1, 0 to 1 the function remains positive and elsewhere it becomes negative, right. So, to maximize its value, we should take only the positive part, this part should go away. So, that means we choose our a to be this point, b to be that point where the function remains positive. So, we choose a equal to 0 and b equal to 1. See, we have not computed the integral, but some geometric argument gives the result. Let us come to the 7th example. Suppose f is a continuous function defined on the closed interval a p. So, as usual we assume that a is less than b. But suppose along with that also we have a to b integral f x dx equal to 0, fine. So that f of x has a 0 in a b, means there is a point c such that f of c equal to 0. Well, the geometric argument we can see first to have the feel what is going on. A is less than b. So, f from a to b are, suppose f is positive throughout a b, then the integral will become positive, it is the area. If f is negative throughout, then its integral also will become negative, but the integral is 0. So, that means at some places f is positive, at some places f is negative, okay. F is continuous. So, by intermediate value theorem f must be 0 somewhere, right. So, that is the argument we are going to give, okay. But we can directly do, because we have mean value theorem for integrals available with us. In fact, that is exactly the proof of mean value theorem for integrals, whatever argument we thought. So, we can now apply mean value theorem for integrals directly. By mean value theorem of integrals, there exists a point c in a b such that f of c equal to 1 by b minus a integral a to b f x of dx, and this integral is 0. So, f of c must be equal to 0. So, the job became easier for us due to this. Or alternatively, you can argue whatever way we have just told, that you can, if you take f x greater than 0 for each this, then what happens? Its minimum exists and is achieved at some point in a b. And also let us say m equal to minimum of f x. Now, m is bigger than 0, then this is bigger than m into b minus a bigger than 0. Okay. So, because we wanted to show if f of x is bigger than 0, then the integral also bigger than 0. And how to show the integral bigger than 0? This is the way. We say that f is continuous. So, since f is continuous, it has a minimum inside the interval a b, which is at some point c, that minimum is achieved. So, we say suppose the minimum is m equal to minimum of f x, then m is also bigger than 0, right. So, a to b f x dx is greater than m into b minus a, which is bigger than 0. Similarly, if f x is less than 0, you would achieve this integral to be less than 0, but the integral has to be equal to 0. Is that okay? All right. So, we will do 1 or 2 problems and then maybe conclude today. So, evaluate the integral minus 1 to 1 2 minus mod x. How do we proceed? So, if you draw the figure, it is 2 minus mod x. So, it is going to point 2 from where it is mod x. So, it will be inverted minus sign, it will be looking something like this, right. So, this distance is 2. Okay. So, you join it will be something this way, but it is minus 1 to 1. So, at minus it will be something like this. This is your minus 1 to 1. So, it is this area we have to compute, fine. So, you can see the polygon now, you join these points and this is the area of that polygon, which is easier to compute. This is minus 1 to 1. So, length is 2, this is 1 and this is same thing as this area. So, you have 3 times 1, right. So, answer should be 3. You can also do directly through the integration. Minus 1 to 1, 2 minus mod x dx equal to minus 1 to 1 2 dx minus minus 1 to 1 mod x dx. Now, minus 1 to 1 mod x dx, we can break that into 2 integrals, minus 1 to 0 mod x and 0 to 1 mod x. In minus 1 to 0 mod x becomes negative x. So, it is minus x, and in 0 to 1 mod x is x. So, this is x. Now, if you just evaluate them using our earlier formula, you also get back the answer as 3. Now, for this integral minus 1 to 1 plus square root of 1 minus x square dx, the square root of 1 minus x square we do not know how to do it right now, but you can use the argument as we have done earlier, thinking of what is this curve and if you know its area geometrically or not. So, in fact, we know minus 1 to 1 square root of 1 minus x square, y equal to square root of 1 minus x square, describe the semicircle of unit radius, right, on the lying above the x axis 0 and this is 1. So, its area is pi by 2. Then you can use the property of the integral to see that minus 1 to 1 dx plus minus 1 to 1 square root of 1 minus x square, which is 2 plus pi by 2, fine. So, the last problem, let us take 0 to root 2 t minus root 2 dt. So, as we remarked, whether it is integral f t dt or f x dx, they are same. So, here again we just compute 0 to root 2 t minus root 2 dt. So, we break into 0 to root 2 t dt minus 0 to root 2 root 2 dt. Then you can apply our earlier formula, that integral a to b x to the power m dx, that formula. So, that gives root 2 square minus 0 square by 2 minus root 2 into, so this one it is a constant. So, root 2 times b minus a root 2 minus 0, which simplifies to minus 1. Okay. So, let us stop here today.